Okay, on this lesson, we're going to be looking at the different attributes of rational functions. So rational, remember, you have a fraction. So there's horizontal, vertical asymptotes. We'll also look at domain and then x-intercepts. So horizontal asymptotes is what we're looking at first. We're going to determine the horizontal asymptote of a rational function by looking at the degree of the numerator and then the degree of the denominator. Degree, remember we've talked about it before, is your highest exponent. Okay, so you're going to compare them. So if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. So if it's smaller on top, it's y equals 0. And then if you're comparing it, the degree of the numerator, if it's equal to the denominator degree, then you're looking at y equals the ratio of the leading coefficients. So you're doing the coefficient of the numerator, coefficient of the denominator. The leading one means the number in front of the highest exponent variable. Okay, and then if the numerator degree is greater than, so it's greater on top, then there's not going to be a horizontal asymptote. Okay, so 3 different things that you need to remember on horizontal asymptotes. Okay, so we are first going to look at our degrees. So the degree of the numerator would be a 2, and then your degree of the denominator is 1. If it's larger on top, remember, greater on top, there is not 1, so you'll just write none. Okay, looking at your part B, degree of the numerator here, highest exponent is 2. Degree of the denominator is also 2. If they're equal, you are looking at the y equals, and then you're looking at the ratio of the leading coefficients. So the coefficient of my x squared is a 2 on top. Coefficient of the x squared on bottom is a 1. You would divide them, you would get 2. 2 divided by 1, which is 2. So y equals 2 is your horizontal asymptote. Remember, if you don't remember, asymptote is where the line's approaching but never actually touching. Okay, so third example, degree of the numerator. Notice the highest exponent's a 1 because we just have an x. And then your degree of the denominator is 2. If it's smaller on top, it's y equals 0. So smaller on top, it's 0. Greater on top, it's none. Equal, you're looking at those leading coefficients and dividing them. So that's how you can find the horizontal asymptotes of a rational function. Now we're going to look at the domain of a rational function. To determine the domain of a rational function, you have to factor first. So you have to factor completely, factor your numerator, denominator, and then after you've done that, you're going to set each factor of your denominator equal to 0 to solve and find the values that x cannot equal. Okay? All right, so first thing is we're going to factor the numerator. So difference of, if you look at 2 terms, difference of squares, sum and difference of cubes. This is difference of squares. It's been a while since we talked about factoring. So when I factor that, that would be x plus 4, x minus 4. The denominator I can't factor, so leave it as x plus 3. So once I factor, your domain of a rational function is all real numbers except what makes your denominator 0, because we can't divide by 0. So if you look at this example up at the top, you can write it with set notation or interval, your choice. I think the easiest is just doing the set notation. So curly bracket, the set of all x's, it's all real numbers except what causes your denominator to be 0. If you need to, set it equal to 0, so that would be negative 3. So x cannot equal negative 3, but it can equal all the other real numbers. Okay, so let's take a look at part B. Factor the numerator, GCF first. They have a GCF of 2x. You're left with x plus 3. Denominator, GCF of x. You're left with x minus 8. And then we are looking at just the denominator to find the domain. It's all real numbers except what would cause it to be 0. Notice there's 2 numbers that would cause this to be 0. So the set of all x's, and your x cannot equal. Here's this piece. If we set it equal to 0, that would be 0. Here's this piece, and that would be an 8. So 0 and 8 would make the denominator 0, which is undefined. So all real numbers except 0 and 8 would be your domain of this rational function. Okay, let's try another one. So looking at C, we can't factor x minus 2. Notice the denominator is a trinomial, so we use sum and product. Sum is the middle, 6. Product is the outside, so that would be negative 16. So that would be what, 8 and negative 2. We don't have to use the swing method because that's a 1 there. So negative 8 times, or negative 2 times 8 is negative 16. Negative 2 plus 8 is positive 6. So your domain is all real numbers except, so the set of all x's, and x cannot equal. Notice this one would be a 2, and x can't be negative 8 there. So to find the domain, just factor. Once it's factored, then you can look and see what would cause your denominator to be 0. That would be undefined, so we know that the domain cannot equal those values. So instead of putting all real numbers except those 2, we can't do that, so we're just listing out the x values it cannot be. Okay. Flip over. Now, sometimes whenever you have rational functions, you're going to have holes in your graph. So holes in your graph just means it's undefined at that point, which means it doesn't include it. So a hole occurs when a factor cancels out on top and bottom because it exists in the numerator and denominator. So first thing you're going to do to find the holes is rewrite your rational function in factored form, paying attention to the factors that cancel. You're setting your factors that cancel equal to 0 and solving. That will give you your x value. So you're using the x value to determine the y value of the hole's location. So your hole is always an ordered pair. So once you find the x, you'll plug it in to the reduced form. To find your y value. Okay. So example 3, first thing, in order to find the holes, we're going to factor it. So looking at the numerator, I can factor x squared minus 16 to x plus 4, x minus 4, and then the bottom, I can't factor x plus 3. Notice we factor completely and nothing cancels out. In order for it to cancel, it has to look exactly the same. So we would not have any holes on this one, because nothing would cancel on top and bottom. Notice these examples are exactly the same as the last examples. So we're factoring GCF, that would be 2x. You're left with x plus 3. Denominator, they have an x. You're left with 8. So notice the numerator has an x by itself, a 2x, and then it has an x here. There's no plus sign or minus sign, so you can cancel those out. Whatever cancels, which in this case was x, I set it equal to 0 and solve. No solving needed, it's just x equals 0. Once I find the x value, that's the x value of the whole, I need to find the y value by substituting that into the reduced form. So I have a 2, and then 0 plus 3 over 0 minus 8. So that will be on top 3 times 2, which is 6, over negative 8, which reduces to negative 3/4. So that would be my y value of the whole. So your whole is an ordered pair. Again, to find the x value of the whole is whatever cancels, set it equal to 0, and then you're plugging that number in to your reduced form to find the actual y value. All right, let's look at C. So factor, can't factor the numerator. Denominator, we've already looked at this, a positive 8, negative 2. Notice x minus 2's cancel. So whatever cancels, I set it equal to 0. My x value of the whole would be a 2. Now, when you simplify this, notice x minus 2's completely cancel on the top, so I'm left with a 1 over x plus 8. Once I find the x value of the whole, I need to substitute it in right here. That's going to give me 1 over 2 plus 8 is 10. So 1/10 would be the y value of the whole, which is a point that is undefined on your graph. So you only have wholes if you factor numerator, denominator, and something cancels out. All right, so we've gone over horizontal asymptotes, domain, wholes. Now we're looking at vertical asymptotes. So vertical asymptotes, identify vertical asymptotes by examining the factors remaining in the denominator after you simplify it. So first thing is to rewrite it in factor form and simplify. Then you're setting the remainder factors in the denominator equal to 0 to solve. Remember to exclude wholes. So we're not looking at wholes, we're looking at the reduced after anything cancels. So part A, I have x plus 4, x minus 4, and then x plus 3. So again, to find the vertical asymptotes, it's what causes your denominator to be 0. So look at your denominator. If I set it equal to 0, the x value would be -3. So there's my vertical asymptote, x equals -3. Okay, so part B, factor. And you have x and then x minus 8. So again, you're canceling anything out that can cancel. Then you're looking at this reduced form. So notice x minus 8, we set it equal to 0. So to make it undefined, that would be an 8. So there is our vertical asymptote. So the vertical asymptotes, again, is what causes your denominator to be 0. Okay, so looking at the next one, we have an x minus 2 on top. We have an x plus 8, x minus 2. So those cancel. So after you have reduced it, you're looking at what would cause your denominator to be 0, because that is your vertical asymptote. So x equals -8 would make this undefined, which means that is your vertical asymptote. It's where the graph is never going to touch. Okay, so again, a lot of information on rational functions. So let's take a look at the back. Now we're going to identify x-intercepts by examining the factors remaining in the numerator after you simplify it. So first thing is to rewrite it in factored form and simplify. Then you're setting the remainder factors in the numerator equal to 0 to solve. And then anytime I have an x-intercept, remember your y value is going to be 0. Okay, so these are the same examples. So we already have factored them. So nothing cancels out. We're looking at the numerator this time, and we're setting each one equal to 0. So that would be -4, and this one would be +4. So writing it as an ordered pair for the x-intercept, we would have -4, 0, and +4, 0 would be your two x-intercepts. Second one, we have a 2x, x plus 3, and we have an x minus 8. Looking at your, remember we can cancel those out, so you have to cancel and then look at your simplified equation or function. So setting this equal to 0, our x value would be -3. So we would only have one x-intercept on this rational function at -3, 0. C, we have x minus 2, denominator factors to x plus 8, x minus 2. Remember those cancel out, so I'm left with a 1 on top and then x plus 8. Anytime I'm looking at the numerator to find the x-intercept, notice there's no variable. If there's no variable or no x, then there's no x-intercept. So there's not one, because we can't set 1 equal to 0 and solve for x. So anytime the numerator does not have a variable x there, we know that there's no x-intercepts, which means your graph will not cross the x-axis. Okay, the last part, we are going to put it all together. First step is to factor. So I have an x in common, that would be x minus 3. And then difference of squares in the denominator, that would be x plus 3, x minus 3. Okay, let's start with our domain, because that's one that we look at before we start marking anything out. So domain is all real numbers except what causes your denominator to be 0 before you simplify it. So our x values cannot be -3 or +3 based on our factored form. Okay, so that one I always look at the original. So very important, original, before you start canceling things out. Now, I'm going to cancel these out. From here on out, I'm going to use the reduced form. So I'll start with the horizontal asymptote. So horizontal asymptotes, to find those, you're looking at the degree. Notice the degree of the numerator is a 1, and then the degree of the denominator is also a 1. So you're looking at this here. So if they're equal, you're looking at the leading coefficients. Notice it would be a 1 divided by 1, so that would be a y equals 1. The vertical asymptotes is what causes your denominator to be 0. Again, we're looking at the reduced form, so we're just looking at this piece of it. So the only thing that would cause your denominator to be 0 would be -3. Again, looking at this piece here. And then let's look for a whole. So since something canceled, we do have a whole. Whatever canceled, which was x minus 3, we set it equal to 0, so our x value of the whole is 3. Once I found the x, I'm substituting it into my reduced form. So x over x plus 3 would be 3 over 3 plus 3, which would be 3 over 6. So my y value would be 1/2. Okay, x-intercepts, we look at the reduced. So notice the numerator, you only pay attention to the numerator. Numerator, we set that numerator, which is just x, equal to 0. So there's our x value, and we know our y value is also 0 because it's always 0 with the x-intercept. So again, it would be helpful to do domain first before you start marking anything out if it reduces, and then the rest of them you're using the reduced equation or reduced function. All right, next one. So I'm going to factor if possible. So my sum is -4, my product's -12. So that would be -6 and +2. Okay, so my domain is a set of all x's, all real numbers, except what causes the denominator to be 0, which would be a 6 and a -2. Then I'm looking at my reduced form from here on out. But notice here, nothing cancels. Okay, so I'm going to go to my horizontal asymptotes, which is checking the degree. Now notice here I have a 1 on top, but notice I would have 2 x's. If you look at your original, the degree at the bottom would be 2. If it's smaller on top, it's y equals 0. So 1 is less than 2. You always compare the numerator to the denominator. Your vertical asymptote is what causes your denominator to be 0 if you have reduced it. So we're looking at both of these. So our 2 vertical asymptotes would be 6 and then also -2. Wholes, we have a whole if something cancels. Nothing canceled, so we do not have a whole in this example. And x-intercept. So looking at your numerator, set it equal to 0. That would be -3. So -3, 0 would be your x-intercept. So there's lots of different attributes to a rational function, so you're having to look at several different things in order to be able to graph these. If you have any questions, please let me know.